Under most circumstances, we can treat a gas as an ideal gas. We'll get later into what the difference is between a real gas and an ideal gas. But for right now, we're going to assume all gases are ideal gases. The ideal gas law is PV equals nRT, where P is the pressure, and the pressure has to be in the unit atmospheres. V is the volume, and the volume has to be in the unit liters. N is the number of moles of the gas, and T is the temperature, and the temperature, just like in the combined gas law, has to be in kelvins. Now R is a constant, the gas law constant. And the reason that I said all of these units for everything else is because R, the value of R, depends on the unit. So the one we are going to use is 0.0821 liters times atmospheres over kelvins times moles. Now, notice that whole batch load of units there is just the unit. It's not a variable. It's not that something has to be substituted in there. It is simply that the unit for 0.0821 is liter atmospheres per Kelvin mole. Think of that as one word, one term. The beauty of the ideal gas law is it's mostly just plug and chug. As long as your pressure and your volume and your temperature are in the right units, you can just put them right into the equation and solve for whatever it is you're trying to solve for. So, for example, if we have the problem, how many moles of oxygen will occupy a volume of 2.5 liters at 1.2 atmospheres and 25 degrees Celsius, it's a pretty easy problem to solve. We simply do PV equals nRT. Pressure is 1.2 atmospheres. Atmospheres is exactly the unit we want, so that's good. Times 2.5 liters. Liters is the unit we want, so that's good. N's the thing we're solving for. R is 0.0821. And temperature in kelvins is 25 plus 273, which is 298. So now I simply plug numbers into my calculator. 1.2 times 2.5 divided by 0.0821 divided by 298, and I find that N equals 0.122 moles. And that's the answer. We can do a little rearranging of the ideal gas law to make it even more useful. Let's think about the ideal gas law. PV equals nRT. Well, N, the number of moles, can also be calculated by saying the mass over the molecular weight. So I can rewrite the gas law to accommodate that relationship, where small m is mass and capital M is molar mass. A little rearranging, multiply both sides by capital M, divide both sides by volume, gets me P M equals little m over volume times R times T. Well, this mass over volume term should look very familiar to you, because mass over volume is density. That gives us a very useful form of the ideal gas law. Pressure times molar mass is equal to density times the gas constant times the temperature. Let's try an example of this kind of problem. If the density of a gas is 1.2 grams per liter at 745 torr and 20 degrees Celsius, what is its molar mass? Okay, so we can use PM equals dRT. But we do need to do a couple of conversions first. 745 torr has to go to atmospheres. We know there's 760 torr in 1 atmosphere. So a quick division gives us 745 divided by 760 is 0.980. 0.980 atmospheres. We've also obviously got the 20 degrees Celsius plus 273, that's 293 K. Okay, now we can plug and chug. 0.980 times M, which is the thing we're solving for, equals 1.2 times 0.0821 times 293. Once again, a quick little calculation. This time it would be 1.2 times 0.0821 times 293 divided by 0.98, which gives us 29.4, and the units there would be gram per mole. Done.